So, that's an interesting story, isn't it? Because now you have sediment that that used to get to the coast by rivers are now getting to the coast by trucks. So, here's a movie to demonstrate globally why 2.3 gigatons of less sediment is getting to the coast. There are two movies. The first one, some of you may have seen. This is every day. Every year, the reservoirs that were developed in the continental U.S., and the data comes from the National Inventory of Dam. You saw the migration of the Europeans across the country and the subsequent damming of the Mississippi River Basin, amongst other basins. This one is the same kind of movie. There's the 1817, 1920, and you will see that there were only a few dams in Japan, India, and then this is a movie of just the very, very largest dams. And so you'll see the American dams. There's a couple in Australia, more in India, the British Empire, more in Europe. Now we see the U.S. filling up Europe, India, Korea, New Zealand. 1950s coming, and you'll see the impact of the great leap forward in China. We are taking out some small dams in the U.S. and a few other countries, but in most cases we continue to build more and more dams. So, if you want specific numbers on specific rivers, I put a few popular river systems of the world for you to look at. From the Colorado, Ebro, Nile, the Yellow, and the Indus, we have the following changes in mean discharge, the maximum flood wave, the change in sediment load, and the change in the concentration, the mean concentration as percentages, the change. And here you can see the years that were picked. These are all moving targets, so if you pick different years, you will get different numbers. In this case, these river systems had losses of both water and sediment. For some river systems, you've changed the amount of sediment getting to the coast, but not the volume of water getting to the coast. The Danube, the Yangtze, Mississippi, and Mekong. The Krishna Po, you're having someplace in between changes in water and sediment, but not as extreme as the top group. And there are still a number of river systems on Earth that are having increases in the amount of sediment. And so you have the following patterns of delivery of sediment to the coast. Sometimes you've increased the load of the river, and sometimes you've decreased it. This is the ratio of pristine sediment load to the Anthropocene load from years before present. This is 1,000 years ago, going to 110 and 1. This is a log scale, and this is a ratio on a log scale. So you have these cycles. Some river systems are increasing in their load, but most river systems are decreasing in their load to the coast. And I should say, these are examples of deltas, the Po, the Yellow, the Ebro, that themselves really should not exist except for human activities. And it's because of human activities a second time that they're going to disappear. So, the next subject is changes in relative sea level. So this is the box model, the balance of sediment to a delta. Changes in relative sea level depend on how much sediment is added to the top of the delta, the aggradation rate. This comes from flooding of the land surface. It depends on what's happening in the ocean. Is the ocean going up or down? In the case of the modern world, it's going up. And it's going up at some rate. The rate is not the same everywhere on Earth. On average, the rate is 3 millimeters per year in the last 15 years. There's the load isostasy. This is, if you have so much sediment, and even the effect of sea level, you're going to push down on the crust, and that itself will cause a subsidence. And on large deltas, this is an important impact. On the Mississippi, it's up to a few millimeters per year, just from the weight of the sediment over the Holocene. Deltas compact, they rearrange their grains, organic matter gets oxidized, and there's a natural compaction rate. And then there's the accelerated compaction rate, what humans do to pump water, oil, gas out of the soil and compress it. And this is written in this simple formula, and if we picked some ideal delta, you would have this, say on average that delta had 10 millimeters per year of new sediment. Sea level was going up under pristine conditions at around 0.5. You had natural compaction of 2, and you had a load isostasy of 2. You would get relative sea level was around 5.5. In other words, sea level was falling or the land was rising because you're adding more sediment than the other changes. But in today's world, we've cut down the amount of aggradation. We've increased the sea level. This remains the same. The accelerated compaction has been increased on many deltas. And this may remain the same. And so now we have a sinking delta. And so this is explained nicely in this diagram that human use, this is from Loicz, human use has a great impact on the structure and surface of the coastal zone. In Bangkok and areas around the Chao Phraya, you have pictures like this that occur because of this differential subsidence. And you have had extreme rates with a bullseye over 100 millimeters per year. Why is this? In this particular delta, you've gone from 1 million to 12 million in 35 years. That's a great change. But there are many other deltas that have experienced large subsidence. The Yangtze, largely due to water withdrawal. The Niger, largely due to oil and gas. The Chao Phraya, due to water withdrawal. And the Po, due to ethane and methane. And so I would like to tell you about what we know about this human accelerated compaction. Because of this methane withdrawal in the 1930s and 40s on the Po, we had a bullseye of subsidence that was around 60 millimeters per year. That's quite fast. Don't forget, sea level is rising at only 2 to 3 millimeters per year. This is very fast sinking. At this stage, they had realized that they were sinking the land surface, and they stopped the methane mining. By 1967 to 74, they did a resurvey. And now we see that instead of sinking at 60 millimeters per year, the rate of sinking had fallen to a bullseye of only 20 millimeters per year. That's quite a recovery in only a few years. They've redone the survey once again, and now we're at 4 millimeters per year, not quite, but almost ambient background conditions. So, humans can cause accelerated subsidence, but the lesson to learn in adaptation is that we don't have to sink these deltas, and we can stop the sinking rate. However, we can't raise the deltas again by pumping into the delta, although that's been tried once. So we end up with a map like this, where deltas of the world have areas of pink, which are areas below sea level. We did a global study. We compared all the sea level stations that were on rock that were around the deltas. And then we looked at the tide gauging stations on the deltas. There was a 4 times difference between how fast sea level was rising as measured by the rock stations as measured by the land. This is a very good indication of the human impacts on accelerated subsidence. Changes in land use have had a profound impact on deltas and their situation, their crises. We don't have time to go into all of these in this talk, but I would like to tell you about a couple. We have stories like the rate of mangrove forests that are being cut in terms of hectares per year. Here we have a rate of around 2,370 in the Vietnamese Mekong coast. And you can see that that rate has been decreasing, and in fact, mangroves are now recovering. Still, the consequences is that huge areas of the coast are now missing their protective mangroves. This is largely because we've had conditions like shrimp farms have been put in, there's deforestation, and I have a story to show you on the Chow Phraya. I hope you appreciate this. This is a picture in 2001. It's relatively recent. You see the shrimp farms, you see the mangroves, and there's a scale, 250 meters. I put this red line on so you can see what the coastline is, so that the next image you will still see the red line. So, 2001, 7 years later. So in 7 years, rates of 250 meters in places. Why? Well, these ponds are quite flat. They have to be flat. That's just how they're built, to be flat. They can't have all the water on one side. So, when there's a breach, the mangroves disappear and the wave, there's some storm that comes in, then you have a huge retreat. So, the human activity here plays an important role in the rate of retreat. It's not just simply the land subsidence, it's the land use that plays a role. In this great book, Gaining Ground, by a number of authors that were once key members of this organization and others, Robert Constanza, John Day and others, David Barker, they put out this book on wetlands, hurricanes, and the economy, and they focus on the Mississippi Delta. From the book, I've taken this. The value of ecosystems on the Mississippi Delta are in the neighborhood of $12 billion to $47 billion annually. The natural capital on the Mississippi Delta is in the $330 billion to $1.4 trillion. So one has to weigh the impact of these vegetation and ecosystem services related to the natural capital, and how this all plays, both of them play into the decision making on the landscape. But we know that deltas have these 500 million people living on them. We can see that in a few examples of population maps. Some of them are heavily populated. We can see that much of this population is in urban centers, that the proportion of the delta that has been converted from forest to land crops is large. and well, you can't see it with the brightness of the screen, roads, systems, and other infrastructures are very large on the deltas. So the human footprint is very large. Each delta has its own story. And so we have systems, all the areas in purple are below sea level on the Pearl River Delta, protected by large barrier systems, coastal barriers, that are protecting it. How well we develop these depends on engineering, maintenance, and the size of the storm that they have to deal with. So changes on storms. This is has been a controversial topic in the global change community. The question is, are the number of typhoons, cyclones, and hurricanes increasing? In numbers, are they increasing in intensity? And we know that the waters that contribute to the hurricanes are warming, and that is the generation for these hurricanes. And from the data, hard to tell definitively, but it looks like they're increasing in intensity. So we will have possibly fewer but larger hurricanes coming in the future. And these hurricanes hit a zone of deltas, mega deltas, where a lot of the people live. So that could lead to inundation of deltas like the Mekong from hurricanes, storm surges. On top of the flooding of the deltas, these maps, these colors are the flooded lands on an annual basis over the last 7 years. So this is the Mekong, this is the Chao Phraya, and so much of these deltas get flooded. This is the cyclone Nargis, this is a satellite image near infrared. All the dark areas is water. You can see it mapped out onto the land surface. These deltas flood. And when we've looked at these, the mapping, we've noted that 85% of the deltas we studied experienced flooding in a short period of time, and over 260,000 square kilometers were below water. And don't forget that there's over 10 million people displaced on the coastal zone on an annual basis every year due to flooding. So what are the strategies for adaptation? We need better monitoring systems. We now can map where the flooding occurs, where the sinking is occurring. We can monitor the discharge from space through the distributary channels, something we were never able to do 5 or 10 years ago. We're now doing that regularly, all over the world. But we need to develop indicators for periodic in-depth assessments. And there is a program that the Transnational Water Assessment Program that we hope to be part of in Loicz family to define what these indicators should be and carry out some of the assessment. We need to define the risks that are on these deltas. And deltas are risky places because they experience the most natural perils. A lot of people are concentrated there, a lot of value. The coastal protection is not perfect. It fails. It failed in Mississippi, Katrina, New Orleans. And the losses have reached new dimensions. This is from the reinsurance industry, weather catastrophes, and the insurance loss trends. So we need more work done on this on a global basis around the world. Where we've defined risk solely on sea level, we've looked at and come up with a scheme that identifies those deltas that are at the greatest peril of future problems, and those deltas that appear that, well, they have some concerns, they're not nearly at the level of other delta systems. And we must look to the future So this is a map, 2009, on the topography of the Mississippi Delta. This is a projection of what the Delta would look like in the year 2100. So, with this in mind, the Army Corps of Engineers in the US are saying, well, maybe we should do this, this, and this, and spend billions of dollars to try to avoid this scenario. So, stopping the conditions with money. There are many people that think, well, maybe we should just abandon this area. That's another solution. Which one makes better sense? That's part of our politics, our governance, and our understanding how we look to the future. So my final slide, I leave you with this. A number of organizations have come together to promote an International Year of Deltas. We would like this to happen soon, hopefully 2013, and this International Year would set up a decade of research, of assessment, of data collection around the world. And we hope you would join us for this, and I'm happy to send you information if you need on this new proposition. Thank you very much.